Before we get started, I just want to remind everyone that after next week's seminar, we'll be hosting a pizza lunch with the presenters. Pat sent out a link a few days ago, and I assume she'll be sending it out again. So please register just so we have an idea of how much food to order. This week, joining us are Salman and Sajad from Miovision, who will be discussing some of their innovative transportation data technologies. They're here from Kitchener-Waterloo, so they made the trek all the way down to 401. And without further ado, please join me in welcoming Salman and Sajad.
Hey everyone. Before we get started, I do have a quick question just to get a better sense of who we've got in the room. Hands up if you're a master's student. So I'm seeing a lot of master's students. Hands up if you're a PhD student. Hands up if you're an undergrad. I have to ask. Hands up if you're a professor. Why the chuckles? That's awesome. And hands up if you're just like a University of Toronto. I was going to say Waterloo. Wow. University of Toronto staff. Excellent. So we're really excited to be here. I know Sajad and I are both academics at heart. Really privileged to be able to come and speak to you students, especially when we think about how Miovision's piece of commercialized technology specific in your realm. It's really a privilege for us to be here to talk to you, so thank you for having us here. Quick introduction about two of us. So my name is Sal, product marketing manager at Miovision. Did my undergrad in science at the University of Waterloo. Actually entered university with that typical healthcare doctor mindset. Much to the dismay of mom and dad, I decided to go into business and did the MBET program at the University of Waterloo. Sajad?
Yeah, I'm Sajad Shiravi. I'm a traffic engineering specialist at Miovision. I work with both the product and the customer success team at Miovision, and my main role is to connect the tech world with the transportation world, and that's my main responsibility.
I'll be the first to say that's a very humble introduction. I think Sajad's the glue that holds Miovision together. Anytime there's a question, if anyone needs a hand, he's literally involved in everything at the company. So, an athlete describes himself as someone who hates traffic, so there's that. So, little agenda. By the end of this presentation, our ambition is when you walk out those doors, you'll know three main things. First and foremost, who we are, who Miovision as a company is, what problems we solve, and last but not least, how we go about solving them. Throughout the presentation, we speckled a few customer case studies, so you can get some real-life applications, understanding of how the tech is being used in the real world. At the end, we might show you some other cool, very localized deployments of our technology. But another fun question for you before we do dive in, hands up if you know the answer to this question, but at an isolated intersection, what's the approximate relationship between the average delay and cycle length?
Signalized.
If you know, throw up your hand.
It's not a trick question. there's this book, so whoever this book, there's it.
Professors, feel free to answer too if you know the answer.
Wild guess.
This is fun. I've never been in the teacher capacity where I'm asking the room and students for a question and an answer. Any thoughts? So John, do you want to give out a hint?
Short cycle length. What happens if cycle lengths are shorter than optimal? What happens if they're longer than optimal?
If it's too short, the average delay will be long. If it's also too long, so there's an optimal.
Exactly. So there you go.
There's the answer.
Professor got it.
So, I don't know if you want to speak.
Yeah, this is just it's supposed to be a fun question, but this is a relationship thing that you got to find. So
yeah. So the reason we asked that question is we actually have a book that Sajad just showed up. I don't know if you want to give it over, but
sure.
It's a book that we as a company publish. It's called Clear Signals,
yes.
And it's specifically on how to use ATS, PMs, and data to optimize your corridors, reduce traffic congestion, and the author of it is Mr. Sajad Shiravi, which is why I say he gave a very humble introduction. Our customers absolutely love that because it is chock full of some really interesting stories. So to give you a brief, little lesson in the history of who we are, Miovision was founded back in 2005, originally as a company that was focused on counting cars. So the story goes that Curtis, our CEO, he was an engineer at the University of Waterloo. Likely you're all familiar, Waterloo is known for its co-op program. And on one of those co-op opportunities, Curtis was sitting at the roadside manually counting cars going through the intersection to be used for a signal retiming project. And he was just sitting there thinking, holy smokes, like I'm a Waterloo engineer, what am I doing sitting at the sides? There's got to be a better way to go about solving this problem. And that was really the genesis of Miovision Scout, our video collection unit, which is used at the roadside, portable to count cars, provides a high fidelity medium of gathering that data that can be then used for signal retiming. What we quickly began to realize is over the course of these almost 15 years that we've been a company, we've been collecting all this video data, and it became clear that we weren't just a counting company. All that video data provided the springboard for a traffic artificial intelligence, which ultimately helped us pivot into our second line of business focused on smart cities. Now, smart cities, very broad, overarching, sexy term in the industry and can mean anything from A to Z. By Miovision, it's our firm belief that smart cities start at the intersection because that's the convergence point of so many things in the city and where you can ultimately provide a lot of benefit to your citizens and everyone else who utilize the roads. We believe that a smart intersection is made up of three main pillars. The first is built off of open architecture. So Daniel was telling us that a lot of folks come into this seminar to help you understand more about the industry. I don't know how privy you are to this, but traffic is very notorious for this idea of proprietary technology, where if you go with one vendor, you're locked in with them, you cannot use other technology, they don't really work well together. Miovision's built on open architecture. We want to be breaking down those walls between vendors and enabling cities to make the most out of all of their existing infrastructure by breaking down those walls. Second is leveraging this ecosystem approach. There's a lot of data out there that can be collected from intersections, and there's a lot of stakeholders that can make a lot of value from that data. So you've got your city planners, mayors, citizens, academia. Professors in the room, this is bread and butter for you. And so Miovision's goal is to be able to have an easy way of sharing that data across all these parties so that we can, again, drive citizen impact. And last but not least, the iPhone model. So when we think back to what the iPhone and smartphones did back in 2007, previously you had all these different widgets or solution-solving point problems. So you had, paper map to find out how to get from point A to point B, probably had a camera, probably had a phone book. The iPhone came along and all of these things became software applications on one unified piece of hardware, and the same way that Miovision's operating at the intersection. Kind of ties into that first piece where we're talking about breaking down those walls with vendors. So with Miovision, one unified piece of hardware, integrate into the traffic cabinet, and we solve a whole host of problems for the customers that we service. So, not as good looking as an iPhone. I guess that's dependent on your point of view, but this is our iPhone at the intersection. So, three main pieces of hardware. So you've got the Miovision SmartLink, that's this first one right here. That's essentially your communications device and that data aggregator that's going to collect information on MMU data, collect information from the controller. The second piece is your Miovision SmartSense. That's really the brains and horsepower behind the entire operation. It's loaded up with 2 NVIDIA GPUs. For those of you who know, NVIDIA has a lot of chips primarily used in the gaming industry. We're actually the first company to bring that type of technology into the transportation sector. It's because of the artificial intelligence algorithms that we're running on our processors. The last piece is the Miovision SmartView 360. It's a single fisheye camera, 4K resolution that enables us to do things like turning movement counts as well as detection. These are the three pieces of hardware, and then on top of that is our software layer, the TrafficLink portal, which is where you can access everything like your data and detection solutions. So, because we solve a whole host of problems, we have multiple solutions. So what we're going to do is, at a high level, talk about the key problems that we solve for the customers that we're servicing, and then dive into some of the solution areas with a little bit more detail. But first and foremost, transportation planning. I think back in the 50s and 40s, about 40% of the world's population lived in cities. The foreseeable future, that number is going to go up exponentially. Every single week, about 3 million people are flocking into a city, and so it's really important to provide agencies with a high fidelity form of data that they can use to ultimately provide those citizens with a positive form of mobility throughout their cities. Second is traffic operations. Traffic operations folks, and Sajad, please correct me if I'm wrong here, very, very resource thin, right? Spread really thin. The region of Waterloo, as an example, there's about 350 signalized intersections throughout the region, with about 3 people in traffic operations to maintain and manage them. So on a given day, very, very busy, very inundated. So how can we find ways to unlock more efficiency in their existing workflow and allow them to accomplish more with less? Congestion mitigation, I mean, we're in downtown Toronto, so I don't think we need to speak to this one much. But, you know, with 3 million people flocking into cities every single week, it's going to become a challenge for cities to try to find ways to promote more capacity with their existing infrastructure. It may not be a simple solution as adding another lane or widening the sidewalks. How can we unlock more potential with the existing data that they have at their infrastructure or in their intersections? And last but not least, traffic safety. So Vision Zero is a big overarching theme in the industry. As we make that push towards complete streets, what type of information can we provide city planners and agencies so they can better accommodate the citizens and have better mobility throughout their cities? So the first solution that we'll talk about is signal maintenance and signal communications. I personally think this is incredible because prior to joining Miovision, I didn't realize the life of someone in traffic operations. So the way a problem is typically uncovered at the intersection is in one of 3 ways. The first is, as a citizen, you can actually call into the traffic department and tell them that there's an issue at an intersection. I didn't realize that was the case, and I don't think most citizens do. And in all fairness, I'm pretty sure traffic operations is relieved that not all citizens know that because they would be getting inundated with calls all the time. Second way is EMS can actually let them know. So if they're out there, tending to an emergency and they see that there's an issue, they can let them know. And the last way is just when they're, observing the streets and going about their drives. They might see that there's an issue at the intersection and tend to that also. Highly unlikely though, because remember, very resource thin, 3 people managing about 350 intersections, not likely to happen. So you have inputs from these 3 different channels. What ends up happening then is the problem that's getting the most attention or that's being yelled about the loudest, that's the one that's going to be fixed. Not necessarily the one that's, causing the most congestion. They go about fixing that problem, don't have a way of measuring the impact of whether or not it was even successful, and they continue down this vicious cycle. In an ideal world, this is what the workflow should be like. Again, as someone totally removed from traffic, I would have thought all intersections would be connected, people in traffic operations have monitors much like you have over there, can remotely access everything. That's not necessarily the case. But ideally, you'd have your infrastructure that could alert you that there's an issue. You'd be able to actually prioritize and rank them and automatically trigger someone to go tend to that issue, which is exactly what Miovision Traffic Link will do for you, specifically our signal communications and maintenance solution. So using our Traffic Link web portal, you're seeing the software application there. All those green dots represent deployments of Miovision's technology in the network. And you can see that there's these red arrows or there's purple notifications telling the person in traffic operations that there's a specific issue at that intersection. Anything from power loss, signals in flash, detectors failing, the whole gambit of issues that they can address. This is actually really interesting because this was our main entry point into the city of Detroit. So Detroit didn't really have a traffic problem. Their issue is more so around infrastructure. Really, really old, dated infrastructure, and they came to us because they wanted to get a little more longevity out of their infrastructure. They used Miovision SmartLink to help them reprioritize and understand where issues were occurring. And we spoke to the traffic engineer there, Sunny, if I'm not mistaken. Really great guy. He was telling us that one of the major pain points was that for them was they were uncertain or weren't able to validate whether a problem was occurring in the field. So they'd get these calls, EMS would let them know. They would actually need to send someone out to verify, 1, that there actually was a problem, and 2, then they would need to get someone to fix it. The reality is, because they were so resource constrained, again, minimal people in traffic operations, they had to outsource that work to a third party, and that contractor would charge them just to go on site. They go on site and there was no problem, they're paying that contractor for nothing. So what they realized was after using Miovision SmartLink and Traffic Link, their contracting costs actually reduced by 50%. So really great ROI for them. They're really happy because now they can remotely monitor and actually prioritize issues at the intersection. The second solution, this ties into that idea of transportation planning and traffic safety, is multimodal detection, continuous counts. We're gonna ask the question, but given who's in the room, this might be a silly question. Does everyone know what detection is? Hands up if you do. Oh my gosh, okay, so I can actually explain it. This is awesome. So in its simplest capacity, detection refers to, when you pull up to the intersection, it's a red light, in a matter of a couple of seconds, you notice that the green comes through. The intersection is detecting that there's a vehicle there, and it's gonna give you the green light to go through the intersection. So if we look at some of the challenges with detection today, there's three main issues. The first is in-ground methods are very limited and costly for cities to deploy. So you've got pucks and loops in the ground that are traditional methods of detection. You need to send out an entire road crew, close off the intersection, cause traffic congestion, and if something does go wrong with them, you've got to dig them up, replace them, do whatever you need to do. So it's very invasive, very troublesome. There's also traditional video detection solutions out there, and they'll often tout that they're the original video solution. The reality is the original ones aren't built for use cases of the future. So a lot of the work that Miovision is doing is around traffic safety and looking at things like pedestrians and cyclists, which is very challenging to do with old technology. And last but not least, being able to justify the ROI. So just like the signal communications example that I gave previously, detection seems like it's status quo, but how do you actually show the impact of your detection solution or your multimodal count solution? So with Miovision, we're deploying artificial intelligence and computer vision, as I mentioned at the outset, with our SmartSense device. This is probably one of the coolest slides I've seen at Miovision, which is you're seeing our algorithms in action. So it's actually picking out individual pedestrians, it's counting the vehicles at a very, very busy intersection. I think this is Toronto, isn't it? It's Bayfront, right? Yeah. So probably one of the hardest intersections to look at, and our algorithms doing a pretty darn good job of it. Continuous counts is another thing that we're leveraging similar technology to do. So turning movement counts for permanent traffic studies, for example, so that on an ongoing basis, cities can do signal retiming projects rather than having to wait those 3 to 5 years. And again, we're able to do multimodal, so whether it's vehicles, pedestrians, cyclists, really, really powerful information, especially for city planners when they look to go about infrastructural projects. I know Toronto is a great example, and I think at the end we'll probably pull up traffic link and show you, but it's staggering to see the volume of pedestrians in Toronto. And I think an insight for a city planner could be perhaps it makes more sense to favor pedestrians in the downtown core. I know we were joking about it on our way in, where it's like they should just close the downtown core to vehicles and force people to walk or use the train, because the streets just aren't built for vehicles. A great example of a use case of our detection and turning movement count solution is the town of Milton. So I'm from Mississauga and I know this region particularly well. They had a lot of congestion right around the corridor where their GO station was. Really, really bad travel times, and I mean, there's metrics associated with it, but you can imagine as a commuter going into the office, the last thing you want to do is wake up, 40 minutes early just because you're stuck in traffic. And on the flip side, getting to your car at the GO station, having to wait another 30 minutes, 40 minutes to get to your house when you've already had a long day at work. What they ended up doing was deploying Miovision, our full stack solution, so detection, turning movement counts, to use the information to promote signal retiming projects, and then use that to actually assess the impact of how effective those retiming projects were. And they found that there was about a 10 to 15% reduction in overall travel time and about a 20% reduction in overall split failures, which, if you're unfamiliar with it, Sajad's going to dive into that now.
Sure. Thanks, Sal.
Do you want some slides?
Sure. That's good. Thanks. So Sal did a great job of explaining our technology stack, right? So how our hardware and software actually enables us to be able to capture a lot of data that's available in the field and bring it in. It is a very, very daunting task because you're dealing with data that has all the characteristics of big data, right? There's high velocity, there's high volume, there's high variety, and kudos to our development team for being able to bring that all in and being able to manage all of that data. But the thing that I'm going to talk about today is okay, so what? I'm going to talk about the so what. The problem right now that the industry kind of faces at the moment is that there's a lot of data being produced from different sources, but when you get to application, it's very thin there, right? So just to showcase kind of that example, I don't want you to read this book, this first page, but I'll just explain what it is. So this is a page from a book called Smart Enough Cities, and then in that book, Ben Green, who was the Chief Information Officer at the City of Boston for a number of years, talks about an example where they had a vendor come in and tell them, oh, we have this massive platform, we're going to bring all of this data for you and all of that, and then when the staff asked, okay, so cool, what do we do with it? They replied back that, oh, I think this is for you guys to go and figure out how you can find value out of this. So that's the dilemma that exists right now, is that there's a disconnect between tech and the transportation industry to be and for government agencies to be able to turn that actually into impact. And then it's kind of a chicken and egg problem as well too, because tech is producing technology, they're trying to move that forward. Of course, along the way they're trying to make money, but at the same time, they have a difficult time to be able to sell to government because they want to see immediate impact, but the tech industry wants to see feedback to be able to kind of improve their solution as they go through. So what I'm specifically going to talk about is one of the pieces of data that we collect from the intersection, which is called ATSPM data. Has anyone heard of ATSPM? Okay, interesting. So, seems like a couple of people have heard about it. So ATSPMs is an acronym for Automated Traffic Signal Performance Measures. This was an idea that came out of Purdue University a couple of years back, and the idea was I would say simple but very creative at the same time. The idea was that there's cabinets at the intersections, and there's controllers, and there's all sorts of hardware at an intersection, and all the signal operation that's happening is happening in this kind of this brain that's happening. Might not be a very smart one, but it is a brain. And then what it does is that it's collecting all of this information from signal status data. Depending on the type of controller, it can get a lot of information. So I gapped out, or I maxed out, or I forced off the amount of green time, red time, amber. All of that information is being logged onto the controller in a high resolution format. Or if the controller can't do that, we have hardware that actually can capture that information. And then there's detector information at an intersection. So as Sal explained, detection or actuation, there's detectors available in the field that their purpose is to be able to manage the traffic, right? And to be able to actuate. That's the purpose of it, but is it possible to repurpose that information? So if the detector is occupied, let's read that information that the detector is occupied. And then I'll go through some of the performance measures, but they had some very clever ways of being able to combine these two pieces of information. So let's say there's an advanced detector on an approach. Maybe it serves some kind of actuation or dilemma zone detection or some kind of other application. And we have the signal status as well too. So as a vehicle is arriving, if you could overlay that arrival with the signal status, you can actually get a good estimate of the number of arrivals on green or arrivals on red, and that kind of information. Or the occupancy of the stop bars can help you get an understanding of how saturated the movement is. And then the third piece that Miovision we have hardware for is travel time. So there's an antenna that goes on the cabinet, and we read MAC addresses as vehicles pass through, and we match those MAC addresses to be able to generate travel time information. So the idea here was that, okay, how can we turn this data now into an actual impact at an intersection on a continuous basis? So the idea that we kind of follow is called like we talk about healthy signalized intersection or corridors, and a healthy signalized intersection and corridor is the one that meets the objective of what the agency has set for a specific intersection or corridor. Different intersections, different corridors, based on in different agencies, in different areas, have different objectives. So in a downtown area, there might be one objective. in a corridor, in an arterial, that the main objective is to be able to move a lot of vehicles, that the objective there might be different. And the whole idea is that we need to make sure that these intersections and corridors are operating efficiently at 3 levels: at a maintenance level, at an operations level, and an optimization level. So when maintenance level, Sal talked about it. Signal needs to work, detection needs to work, communications need to work, and if you don't have that, you can't build on top of that. So if you have the best optimized plan in the world, if one of your detectors is stuck on and it's not working, that optimized plan makes no sense, or it's not going to work in the optimal manner. That needs to work properly, right? And then at the operations level, this was actually an interesting level that we figured out after analyzing a number of intersections, was that a considerable number of intersections in the United States and Canada didn't even have the prerequisites to an optimized plan. So what do I mean by that? So for example, a coordinated corridor, all the intersections along the corridor, if it's coordinated, they need to operate on the same cycle length. This is very, very obvious, right? And then in 70% of the corridors that we looked at, 1 or 2 intersections, by mistake, by error, were operating on a different cycle length. For 5 years, 10 years, this was going on. So very, very basic issues. So, or other very basic issues. So let's say there's a left turn movement, it's not gapping out properly. It's on either on recall, it's wasting green time, minor movements aren't terminating properly. So a lot of issues just at this level. At the optimization level, now the next level is optimization. So based on objectives, how can you optimize in order to create more efficient operations? And the reason why continuous data makes a lot of sense is that, let's say a major signal retiming even happens. Let's say the traditional way, I go out, I collect the turning movement counts, we put in a new timing plan, right? So the health rating is pretty high at that point. It's efficient, we found the problems in tuning. So as time passes by, things happen, and we've seen that through thousands of intersections that we've been installed at, is that after a while, there's a detector failure that happens. After a while, there's a clock drift, so one of the intersections actually starts to drift in terms of the time. So if it drifts, it means that the intersections, that the coordination can't keep the offsets in line based on design. Where after a while, there's change in behavior. There's this left turn movement that now has more traffic because of this, I don't know, new Costco on this approach. So this is why it's important to be able, as time passes by, be able to identify these and correct them incrementally as time passes by, not to wait 5 years and then find a ton of problems with lots of inefficiencies and don't fix them. So I'm just going to go through a pretty simple example here around how one of our installations uncovered a number of issues and how it was able to create more efficient operation using the data. So this was a corridor. It was in Charlottetown PEI. It's a very Charlottetown PEI gets a lot of tourist traffic during the summertime. So there's lots of seasonal traffic that's happening. And then the aim was there's lots of citizen complaints coming from this corridor, and with Miovision hardware was installed at these intersections to get a better understanding of what's going on, what's the severity of the problem, is there something that we can do about it?
Just to provide a little bit of color, the specific case study here, Charlottetown PEI, what we found was, Sajad mentioned, summer months, tourist town, we were actually seeing a 3,000% increase in vehicle volume, specifically along this corridor. So I mean, put that into context, a 3,000% increase. Good returns if you got that in the stock market, not something that you want to be dealing with if you're traveling along that corridor.
So when we installed, we wanted to get an understanding of what's going on, right? So performance-wise, along the corridor, what times throughout the day are we seeing issues? What's general performance? Because sometimes even perception is different from a citizen's perspective than from a holistic perspective. So what you're seeing on the screen is one of the graphs that we provide. It's from travel time information. It's called the congestion scan. So I think it's a very, very good graph to be able to visualize travel time along these different sections of a corridor on a 24-hour duration on both sides of the corridor. And then what it's visualizing the travel time index. So the median travel time over the free flow travel time. And then that kind of gets rid of the distance factor of it. So it makes it comparable. So as you can see here, it's very, very obvious that throughout the day, performance seems to be quite well on the southbound approach, generally throughout the day. On the northbound, morning seems to be okay, noon somewhat okay, and then during the PM peak, there's a very, very specific time that travel times are 4 times, 5 times free flow travel times. So it's fairly obvious like when this is happening, and not only this isn't only happening on one day, it's a trend. So that's a good thing with continuous data. You can get weeks and weeks of data and be able to identify trends out of the data, not just like one day. And then once you find the problem, you can, well, not the problem, like the area that you want to focus on, there's data there to be able to easily understand, okay, what is the controller doing during that time? Okay, let's go and see what the controller is doing. So all the controllers, the graph that you can see on the screen is called a phase interval graph. It's actually showing you the cycles that are happening. What you can realize from this quickly is that cycle lengths along the major approach are variable. This is a sign that this is not coordinated. It's not operating on a coordinated cycle length. But the interesting observation here is that although it's not coordinated during the times where the problems are happening, cycle lengths are actually quite high. It's in free mode operation, so intersections aren't really paying attention to each other, and they're operating in isolation from each other. But the interesting side is that what was the objective that you wanted to reach by allowing these to operate in free mode? If it was to create less delay for miners, well, that's not happening. There's large cycle lengths that are happening. Like, what's the point here? So that's you can start to identify. Okay, are you reaching the objective that you wanted to achieve for this objective during this time or not? Data is showing you you're not. Technically, you're not reaching it. So and then what the data is also showing is that during the heat of that time, where travel times are maybe 5 times, 6 times the free flow travel time, you have miner movements that have very short amount of green time. So the major is very busy. There's one vehicle that comes on the miner, immediately services that miner movement and creates a lot of delay for the major movement. This could create a lot of downstream green starvation and issues as well too. So lots of short interruptions to the major. You're not allowing a nice queue to build up on the miner movement. This is another graph that we produced from the data. It's called the time-space diagram, as you all know. But this is an actual time-space diagram, right? It's not theoretical. It's not based on. So this is actually how it's happening in the field, right? So as you can see, obviously they were operating in free mode. There's no coordination going on. Very likely that downstream, the upstream intersections downstream is green, upstream is red, creating lots of green starvation issues for downstream intersections, and you can see, you can get a better visual of what's going on here. So to this point, we understand that PM peak experienced significant delay, lack of coordination. There's randomness in operation, major interruption to the major. Data also shows that throughout the entire day you're good. There seems to be like a 1 hour, 2 hour duration where you have problems during the PM peak and towards the northbound direction. And the data indicates that likely coordination can help. So the same data that we talked about can now inform a new timing plan. The natural cycle lengths that were happening, you can use them. You can use the splits that were happening, and by using a software, for example, like Synchro, you can actually, so without the need to actually add turning movement count for each of the intersections, you can put a cycle length, you have your splits. It's just a matter of optimizing your offset based on directionality. One of the intersections had a smart sense device, so it was giving us volumes in terms of directionality, and we're able to use that to be able to optimize the offset. So after the change, they put in coordination. The city, you can see, northbound is favored in terms of coordination. Time-space diagram is now in favor of the northbound direction. They decided to go with 3 to 6 p.m. in order to address the situation. After the change, now this is the fun part. You get to evaluate what kind of impact this had, right? So what's the worst that could happen? The worst is that you just go back to whatever you had, right? So let's evaluate the impact. So in terms of traffic volume, there was actually around a 3% increase in traffic volume between the before and after evaluation that we did. And we can go back to the same graphs that we found the problem to be able to evaluate the impact. So after the change, you can clearly see that based on a trend, the PM peak is actually operating in a much better, much lower travel times in general. I'm not going to go through the details of this, but there's all sorts of different metrics to be able to quantify that impact, right? So the travel time, the increases, and then being able to quantify what kind of impact that had, and then being able to quantify what kind of impact this had on all the movements at an intersection, not just the corridor itself. So, for example, what was the impact in terms of the number of split failures that were happening? And so most of the intersections were actually experiencing a decrease in the number of split failures. So this actually benefited the miners as well too. And then, as expected, there's a bit of an increase in the delay of the miner movements. This is a trade-off that we accepted for one of the movements to be able to enable coordination. Then all of this information can go into we can quantify the impact in more tangible formats as well. So cities, or I'm not going to say cities, but higher officials in cities may not completely understand, like, oh, this is, they understand travel time, they might not understand coordination or all these split failures and that kind of wording. So it needs to be converted into a more tangible format. So what does that mean in terms of savings? What does that mean in terms of delay savings? What does that mean in terms of emission savings? There's models, of course, coming from academia, that you can use travel time and counts and changes in that to be able to convert that change into an actual savings estimate. So this is my last slide. I just want to go through. I just want to explain that this was very vehicle focused, right? Because the objective there was to create coordination, keep the corridor moving. What we're thinking about at the moment, the detection that's available in the field and the traditional kind of view of the traffic network has been mainly vehicle focused. But what about other modes of traffic? So our SmartSense device, we're detecting, tracking vehicles, pedestrians, cyclists. We have signal timing information. There's a whole new opportunity to be able to generate performance measures that quantify not only the vehicle's performance, but now the pedestrian's performance, the cyclist's performance. So just to give you a very simple example, when a pedestrian is passing the crosswalk, we're counting them, there's a timestamp associated with that. We have the signal status data, so we can actually say how many pedestrians were actually compliant, non-compliant, how many passed during walk, during flashing don't walk, what happened during that time. You can go back to the video and actually observe when a problem happened, when a non-compliance happened, what's the reason behind that, and there could be safety applications. So you can imagine like being able to actually see more at an intersection or in the road network, along with information that's coming from the controller, it creates a whole new opportunity to be able to generate performance measures that now quantify the performance of the network from a multimodal perspective. Yeah, and then if you want more examples, there's a Clear Signals ebook. It's full of these kind of examples around how the data can be used, and real examples. If you go to atspms.com, you can download the ebook. It's for free. And let me know if you have any feedback on this.
Sajad, a quick question. Many of you didn't know what ATSPMs were. Do you have an analogy, super digestible, if someone were to ask them on the streets, hey, what are ATSPMs? What's a good comparison?
Okay. So ATSPMs, I would say, it's like an MRI for the traffic network. I would say, like performance measures in general, right? Like it's similar to when you have a headache, you go to doctor. Doctor might prescribe an MRI just to see what's happening in the background, right? To be able to prescribe something. Understanding whether you can do something about efficiency or whatever objective that you have, you need to get a better understanding of what's happening. And I think ATSPMs is more of that MRI that you kind of run on your traffic network to get a better understanding. Okay, what's going on?
So it's helping you diagnose what the actual issue is so you can prescribe the necessary solution.
Yeah.
They love that. I did my undergrad in kin, so any healthcare analogies always stick well with me. Yeah. But that about sums up our presentation. Just 3 key takeaways for you. I hope, as you walk out those doors, as we discussed on the agenda, you know who we are, problems we solve, and the way that we go about solving them. But just to wrap it all up, at the highest level, what Miovision does is we're helping cities solve traffic problems, right? We're doing this by unlocking data from the intersection, we're pioneering the use of artificial intelligence, and we're using open architecture. And the last takeaway for a lot of you, especially if you're on the cusp of graduation, is we are growing aggressively in the next year. So I don't think it's all that often that you get to interact with a company that's commercialized technology in the space. So if you are interested in learning more about Miovision, feel free to talk to myself or Sajad.
Yep. And we're also interested in working with academia as well. So definitely academia is what drives this. So the whole ATSPL idea came from academia, right? So and then this is just the beginning of the data era, I would say. And then we really appreciate working with academia to be able to move this forward for sure.
Any questions?